Section 9.4, improper integrals. The first thing we need to discuss, quiet please, is the meaning of an improper integral. There are two types of improper integrals. The first is what we see here, and that is when we have an upper or a lower limit, or both, on our integral being infinity or negative. All right, so an improper integral, the first type that we're dealing with, we have an infinite upper or lower limit, or both of them are infinite. So here we have the upper limit being infinite, here we have the lower limit being infinite, and here we have both. Take a second and copy that down, and then we'll talk about it. So what makes these integrals improper is the limit being infinite, and we consider that improper because when we evaluate a definite integral, we take the antiderivative, we plug in the top limit, we plug in the bottom limit, and we subtract. Well, there is no actual value infinity. Even though it's L'Hopital, we keep thinking about plugging in a huge number. What we're really doing is taking the limit. What is this approaching as x gets huge? So in this case, to address these infinite limits on our integrals, we need to bring in a limit. So if our upper limit approaches infinity, we need to replace it with a variable and take the limit as that variable approaches infinity. All right, same thing happens when the lower limit is negative infinity. We replace that negative infinity with a variable and take the limit as that variable approaches negative infinity. Let's think about what we are actually finding. If we have an integral from a to infinity of f of x dx, what we're really looking for, oh boy, is the area under the curve of some function from a forever outward, like this. And that area could approach a finite value, or it may not. So, generally speaking, if the function converges at the end towards some value, quick enough, then our area could approach a finite limit. But if it doesn't, like this one is going to go up forever, then the area under the curve would be divergent. All right, so when we do any of these three situations, if our actual integral comes out to equal some value, then we would say that the integral converges to that value. Okay? If at any point in our process our integral comes out to diverge to infinity or negative infinity, then the integral diverges and we are done. We cannot calculate the area under the curve. Okay, so this first situation is from a to infinity, so it's like the graph that we have here. The second one would be from negative infinity to b. So we would be looking at trying to figure out that type of area. And then the third situation is from negative infinity to infinity. So if we have something that looks like this, we're looking for all of it. The area under the entire curve. Okay? This third situation, if I go from negative infinity to infinity, then what we need to do is pick some value in the middle where our function is defined, and Kate may choose a different value than Malachi. Doesn't matter, as long as we are going from negative infinity to that value, and then from that value to infinity, we will have the entire area with the sum of those two integrals. Okay? So when we have it set up where it's an integral from negative infinity to infinity, we rewrite it as the sum of 1 and 2. Okay? So let's try some examples. Our first one, the integral from 1 to infinity of 1 over x squared dx. So what makes this an improper integral? The upper limit. So that's the one we need to replace with a variable. and I'm going to choose p. So as p approaches infinity, the integral from 1 to p of 1 over x squared dx. So on each of these, please do not drop the limit in anywhere in your process, because that's what tells me you know it's an improper integral, and we can't just plug in infinity. And the other thing I suggest is off on the right, do your actual integration, and do it neatly where I can find it. This is the integral of x to the negative 2 dx, which is what? Negative x to the negative 1, which is negative 1 over x. It would be plus c if we were doing the indefinite integral, but we're doing a definite integral over here, so we don't need our plus c. So, any time we are involving this p, we need to have the limit in front of it. So, we have the limit as p approaches infinity of negative 1 over x, evaluated between 1 and p. And now we just continue with fundamental theorem, remembering our limit. So we'll have the limit as p approaches infinity of negative 1 over p minus negative 1 over what? 1. All right. What will this approach? 0. This one's going to 0 minus negative 1. So our answer is 1, and we would say that this integral converges to 1. And we are done. All right, any questions on what we did on this one? All right, we're just going to do a bunch of examples. These are different examples from in your book, so you can use your book examples for extra practice as well, or extra help. So, I chose I chose 1 over x squared and 1 over x because when we get onto series, they're two very useful series. So I want to play with them a little bit when we are in sequences and improper integrals as well. All right, determine if the following integral is convergent or divergent. If it's convergent, find its value. So please do it at your desk, very similar to the one. All right, so our upper limit is what makes this improper. So we will have the limit as p goes to infinity, the integral from 1 to p of 1 over x dx. And we'll take our actual antiderivative over here, and what do we get? Yep. We get the natural log of the absolute value of x. So over here I will have the limit as p approaches infinity, the natural log. Do I need the absolute value of this?
Yeah, well, that didn't.
But it's never wrong if you put it in. So I'll keep it in, even though we don't need it this time because we're going from 1 to infinity. They're all positive. But I'll keep it in. So here we get the limit as p approaches infinity, the natural log of p, or the absolute value of p, minus the natural log of 1. We don't need a limit on the part that we do with the constant. We just need it on the part with the p. So, what happens as p approaches infinity on the natural log curve? Goes to infinity. So here we have infinity. This is divergent.
Wait, how do we could cut the absolute value?
No. The absolute value, just make sure we're not plugging in values that are negative because natural log is not defined over here. So it's just making sure that we're taking the log of a positive value. All right. Anything else on this one? Okay, let's try another one. Nope, I don't want that one. I want this one. All right. So what makes this one improper? Both the lower and the upper go from negative infinity to infinity. So this is the one where we need to set up two integrals. We're going to set up an integral from negative infinity, and when you choose your value, make it easy. 1 or 0. I went to 1, I think. x e to the negative x squared dx plus what integral? 1 to infinity of x e to the negative x squared dx. And then we'll add in our limit. Plus the limit as b goes to infinity, integral from 1 to b of x e to the negative x squared dx. And we need to do our actual integration, our actual antiderivative of x e to the negative x squared dx. How do I do that? U sub. Let u equal x negative x squared du negative 2x dx. So I'm looking at negative 1/2 du equal to x dx. I've got negative 1/2 the integral of what? E to the u du, which gives me negative 1/2 e to the u. I would have a plus b, but we're really doing a definite integral here. So this is negative 1/2 e to the negative x squared. So that's what we will be plugging in over here. Limit as a approaches negative infinity of negative 1/2 e to the negative x squared, that's an x, evaluated between a and 1, plus the limit as b approaches infinity of negative 1/2 e to the negative x squared, evaluated between 1 and b. At your desk, figure this out. I want to know if it's convergent or divergent, and if it is convergent, what is the limit? Or what is the b? So, if I take the limit as a goes to negative infinity of this value, first I will have negative 1/2 e to the negative 1, correct? Minus, and here's where I need my limit, the limit as a approaches negative infinity of negative 1/2 e to the negative a squared. Plus the second one, which we'll do in a minute. Alright, so this is just negative 1 over 2 times 1 over e. What is this? So when I put in a gigantic negative number for a, and I square it, I get a gigantic positive number, and then there's a negative being multiplied. So I have e to a gigantic negative. Exactly. So down here I'll put a little note. E to the negative infinity means 1 over e to the infinity, which means 1 over a gigantic number which will approach 0. So, minus 0. Okay, so there's that first half. Plus, this time, our limit comes first. The limit as b goes to infinity of the same thing, negative 1/2 e to the negative x squared, b squared. You're right. You're right. Minus negative 1/2 e to the negative 1. All right, so on this one, what happens? The same thing, right? We get infinity squared, negative in front of it. Again, we have e to the negative infinity, which is 1 over e to the infinity, which approaches 0. So now I have negative 1/2 times 1 over e plus 1/2 times 1 over e, giving us 0, which means it converges to 0. Okay. All right. So the next thing I want you to put into your notes is not all of this. You have a table like this in your book, slightly different. I chose a different one. What I would like you to put into your notes on this page is whatever I write. Okay, so you don't need to rebuild the whole thing. But it is our second type of improper integral, which is when we have a discontinuous integrand. So what does that mean? Well, it means we're doing something like trying to find the area of something like 1 over x squared, which is the volcano curve, from maybe -2 to 2. So we have a discontinuity in the region that we are trying to find the area of. Okay? Sometimes, again, this will converge to a finite number, and sometimes it will not. So in these types of improper integrals, we may not have infinity. So you have to think about what makes the function discontinuous, or what makes it undefined. All right? So we'll talk about, I guess we'll talk about all 4, but the first 3 are the most important. The first situation is when we have the integral from a to b, and we are not continuous at b. So this is what I want you to write, not continuous at b. So that means we have from a to b with a parenthesis on the b. And to do this, let's give a picture of what we're looking at. From a to b, we're defined at a, we are not defined at b. So to be able to evaluate this integral, we need to add a limit on our b value, and we can only approach b from what side? The left. So our integral will now be the limit as, we'll call it p, approaches b from the left of the integral from a to p of f of x dx. So we put the limit on the undefined portion. And you need to think about which way can I approach it from. All right? So our second option is not continuous at a. So this time we're looking at parenthesis a and a bracket on b. So our picture, I'm sure you can come up with from a to b, would be something like a hole or an asymptote at a, and we are defined at b. So now I can only approach a from the right, so that's the type of limit we need to put on here. So we are going to do the limit as, we'll say, I don't know, d approaches a from the right, integral from where to where? b to b of f of x dx. Our third condition is when our discontinuity is in the middle. So it could be something like this. Okay? And just like we did with our first type of improper integral, for the situations of 3 and 4, we rewrite it as a sum of the situations of 1 and 2. So here we would have, to figure out this integral, we would set up a number 1 plus a number 2 integral and evaluate them. So we set up one that has a limit coming from the left and one with a limit coming from the right, and then we would evaluate both. The final one, we would do the same way, but this time we're undefined at our endpoint. So we still would set up a combination of number 1 and number 2. to evaluate that area under the curve. Okay? So the process is the same, it's just our limits are set up around different values. All right, so let's try one. Let's try this one. Sorry. Okay. Determine if the following integral is convergent or divergent. If it is convergent, find its limit. So what makes this an improper integral? Undefined where? At 3, which is the b value, yes. So this value is what makes this undefined, because it gives us a 0 in the denominator. Okay? So that means that's where our limit has to happen. So we're looking at the one that is similar to this situation. Right? Where we're undefined at the right end. So we'll have the limit as p approaches what? 3 from the left. Integral from 0 to p of 1 over root 3 minus x dx. Now, don't worry about the left, handling it from the left until after you have done all of your work and you're evaluating your limit. You still want to plug in the 3 first. If it works out with plugging in the 3, that means that limit exists from both sides and we're fine. If you run into trouble when you plug in that 3, that's when you want to think about what's happening if I come from the left. Okay, so treat it like that left, that negative is not there until the end. Okay, so go ahead and do this at your desk, please. All right, go ahead and look up. I got that we converge to 2 root 3. Do we agree? Any questions on any part of it? I had a couple questions earlier today about why I have a 2 here. Why do I have a 2 here? Because I applied the power rule for integrals to get u to the 1/2 over 1/2, same as multiplying by 2. Any other questions? All right, we have one final one to do. And, yeah, oh sure, yep, sorry, get going. I think the one I want to look at is that one. Yes. Let me see, I'll make it a little bit bigger so you can see the limits a little easier. So we are doing the integral from 0 to infinity of 1 over x squared dx. Take a minute and think about how to set this one up. So since we are discontinuous at 0 and we have an infinite limit, we have 2 reasons that we're improper, and this is one of these situations where we need to write 2 integrals. So we will have an integral from 0 to, I don't know, 10. You can choose 1, whatever you would like, of 1 over x squared dx, plus an integral from 10 to infinity of 1 over x squared dx. And now we'll bring in our limits. As a approaches what? 0 from the right, actually, because the 0 one is like this one. So we can only approach a from the right, okay? So it'll be from the limit as a approaches 0 from the right, the integral from a to 10 of 1 over x squared dx, plus the limit as b approaches what? Infinity, integral from 10 to b of 1 over x squared dx. here we are again with the integral of x to the negative 2 dx, and we get negative 1 over x. All right, limit as a approaches 0 from the right of negative 1 over x evaluated between a and 10, plus the limit as b approaches infinity of negative 1 over x from 10 to b. All right, so we plug in, we get what? Negative 1 tenth. Sorry? So I'm going to write minus the, we need to keep limit in here, minus the limit as a approaches 0 from the right of negative 1 over a. So what's that going to go to? We are done. That's going to go to infinity. This is divergent.
But I know what to keep the limit.
Anytime you're dealing with the variable that is involved in the limit, you need to keep that limit statement with it. So when we've dealt with b over here, we would need the limit in front of that. If you're just dealing with the constant, you don't need the limit. All right, homework for tonight, section 9-4, 1 through 29 odd. That is what I have on the website as well.